good morning, all of you. We will start from the point where we left. We were doing this Nyquist criteria for ISA avoidance. Now, if we talk about by the name, the Nyquist criteria for ISA avoidance, it seems that this is a concept which has been put on us unnecessarily. It means, why are we doing it? So, this stems from the simple, you can say, signal processing principle, or what you will assume will happen in reality. See, whatever channel over which you will transmit your pulses, okay, most probably that channel will be band limited. Band limited means that it will pass a few frequency components without any distortion, and the remaining it might distort, it might suppress, or it might even don't allow them to pass, or just you can say it attenuates them very heavily. Now, because of this, what will happen that the time spreading of signal takes place. Now, when time spreading of signal takes place, so all the pulses, because you are assuming a pulse-based communication system in which for a bit interval you generate one pulse, maybe multiply it by the message encoded thing, or you just change the phase of the pulse, or whatever something you do based on the message, whatever you have to the pulse for the bit interval. Now, if the pulse which is there in this bit interval gets smeared with the pulse which needs to follow, or the previous pulse, so this is basically called as the ISI. This will happen because you are transmitting the pulses over band limited system. Over the band limited system, the frequency spectrum gets clipped, and because of this clipping in the frequency domain, time luminous pulse will expand. Once they expand, they will start interfering with the nearby pulses. Now there is a big trouble with the detector then, because then the detector has to do a very good job in extracting the information without any error. Okay. So he studied this problem and he gave three criterions. That's why the name comes Nyquist criteria for ISI avoidance. Okay. So ISI avoidance is what is the problem we are going to solve. Basically, he solved, and that's why the name became Nyquist criteria. Okay. So we saw that. I think let me just go to the point where I want to refer to. Yeah, we saw that why not, if at all you are saying that time limited pulses. We studied these two cases. One is that if at all there is a problem with the bandwidth being larger, why don't we have a restricted bandwidth pulses? It means those pulses which are within the band of the channel on which we are transmitting. It means suppose the channel is band limited to W hertz. So why don't we have pulses which are inherently band limited to W hertz? Okay. So we studied these two cases. One is if we have time limited pulses, then they cannot be band limited, and hence they will be ultimately suppressed by the channel. So this doesn't solve the problem. And what if you use band limited pulses? Now the problem with band limited pulses is that they will have a large time spread. So in any ways, without even transmitting over the channel, we have ISI. Okay, but they cannot be time limited. Still, overlap happens, and ISI cannot be avoided. So finite transmission bandwidth leads to ISI anyway. So this is what was the important conclusion, or the important starting point of our last lecture. Then we said that if at all we allow the pulses to overlap, but in a controlled manner in the time domain. Okay, but this way we will have band limited pulses. We will have time. We will have pulses in time that extend from, let us say, that extends over multiple bit intervals, but still they do not lead to ISI. Okay, so that is what we say. Pulses are allowed to overlap, yet shaped to cause zero ISI. Okay, with all the other pulses at the decision making instance. So this is important. Ultimately, जिस रेट पे और जिस पॉइंट पे विल बी सैम्पलिंग द सिग्नल, अगर उस पॉइंट पे मेरे पास इंटरफेरेंस नहीं है तो देन आई एम हैप्पी. आई शुड बी हैप्पी बिकॉज ultimately my job is to detect the message, not to detect the pulses or not to generate cleaner pulses right now. Okay, first of all I need to detect, and if I need to regenerate, so I will regenerate fresh pulses from those detected messages or information. Okay, so that was the you can say the underlying principle behind Nyquist's first criteria, that you allow the pulses to overlap, but at the sampling instance they should not lead to any ISI. Okay, so this was the first criteria for zero ISI. So the requirement for the same was that the pulse P of t should have, let us say, should have a zero value at the other sampling instance, or sorry, at any sampling instant, let's say TB, 2TB, minus TB, minus 2TB, but at the 0th point it should give a non-zero value. We have not yet specified what is the value between 0 to TB. I think I have written this so that you are not confused what sort of pulse design we are doing. We have just specified this is a continuous function of time, We have just specified it at some discrete points. Okay, we are not yet saying what will happen between 0 to t. It will definitely take some value. Okay, so that I have written last time. Okay. Then we came to an important theorem that was we took it from the this dimensionality theorem, and I referred to lecture 10 for this. If you can go and see lecture 10 back, you will realize that we found out that for r bits per second, if you need to transmit this, if this bit rate we need to transmit over some channel, then minimum you will need a bandwidth of r by 2 hertz. Okay, this is important to remember for the lifetime, that for r bits per second minimum, this is the theoretical minimum. इतना होता है या नहीं होता है, that depends upon our pulse shape. Okay, whatever pulse shape we will be using, that will basically dominate the frequency consumption, or that will dominate the bandwidth consumption. But theoretically minimum आपको r/2 चाहिए, r/2 से नीचे आप नहीं कर सकते. Then we found out क्या कोई ऐसा pulse है, is there any pulse that really takes only r/2 bandwidth and gives us a bit rate of r bits per second. So answer was yes, that was the sync pulse. Okay. So in the time domain you have a sync pulse, and the frequency domain you know that it is a very band limited pulse. It only extends from -b to b say. Okay. And this is what we saw, that r/2 ही इसका bandwidth consumption है. Base band में, I think I must have written here at the base band. Somewhere I had written base band. So this is important to know, that at the base band the bandwidth consumption is r/2, and we know that it is band limited. So our work should be done. But there is a problem, or there are 2-3 problems with this sync pulse in the time domain. Okay, what are those problems? One is that you have to wait infinite time to generate this pulse. First of all, मतलब ये pulse जो है, you know that it extends from -infinity to infinity. It is not time limited. It is time unlimited pulse. Okay. Now what happens if we truncate it? So if we truncate it, then the bandwidth will obviously increase. If you will truncate in time domain, then frequency domain, the bandwidth consumption would increase, and the pulse will definitely consume bandwidth more than r/2. And this is the main motivating factor behind the design of raised cosine pulses, which we will be doing. That the decay of this sync function is with the order 1/t. It means it slowly decays. So the issue is that if you have a disoriented sampling time, so अगर आपने correct synchronization आपका अच्छा नहीं है, आपका sampling time थोड़ा सा गड़बड़ है, means there are 2 issues. One is that if your sampling time is of problem, or if your sampling interval is of problem. So if in both the cases, other pulses will lead to severe ISI. Now why do we say this? Because of this term that I think you must have read in sequence series, that summation 1/n is not summable. That is, it can lead to very high values. अगर हम sum करेंगे इसको, तो बहुत large values हो सकते हैं. तो क्या होगा अगर आपका sampling time properly synchronized नहीं है? If it is not synchronized, so what will happen? Several of the pulses will add, and if they all will add, they can lead to very large values. Okay. So it is it becomes very difficult to detect the message or detect the information symbol, whatever you say it, correct. Okay. So then we said that what can we do? Can we have pulses which have a better decay? So I think that is what we started. This is what we do. But before we start with that, let me just write down a few important things which I feel you should. No, I am taking it from I think Upamanu Madhav's book. Well, he presented this thing very beautifully, so I thought let me share it with you. So we call this sync pulse is the minimum bandwidth. So sync pulse is the minimum bandwidth Nyquist pulse. Okay. So this we have seen. Why do we call minimum bandwidth? Because theoretical minimum was r/2 for a transmission of r bits per second, and the sync pulse is basically that pulse which really takes the minimum. Okay, that's why the name comes minimum bandwidth Nyquist pulse. Now the role of excess bandwidth. Okay. What is the logic behind considering bandwidth greater than r/2? Because the minimum bandwidth was r. So the point is that if you want, let us say this is a slowly decaying function. Suppose this is a slowly decaying function. And if you want, let me just write again to have a better picture. It means suppose suppose this is slowing decay, slowly decay. It means that this, and if you want a function which is like this, that is this decay is sharp. Now, because you are having a sharp transition in the time domain, the corresponding impact, if this the bandwidth was this, suppose, then you need to increase the bandwidth. If suppose this is your 0 and this was your r by 2. So if at all I need to have a sharper transition in the time domain, I need to have frequency components of a greater value. Okay, means ज़्यादा frequency components को लेना पड़ेगा सिस्टम के अंदर, जिससे हम टाइम डोमेन में शार्प ट्रांजिशन को अफोर्ड कर पाए. तो जनरली अगर आपको ऐसा पल्स चाहिए जिसका डीके रेट t⁻p हो, that will definitely consume more bandwidth than r. So जो minimum bandwidth तो नहीं रहेगी. Okay, that is what I think the raw length should be the whole. So this is what is the I think the underlying principle behind what we said here, that it consumes. I think I must have here. Ben Nyquist showed that such a pulse requires a bandwidth which is k r by 2 with k lying between 1 to 2. It means this pulse will definitely, if this pulse has a decay rate which is larger than 1 by t, it will have a greater bandwidth consumption than r by 2. Okay. Basically, we will do this in the theorem, but because the explanation given by this textbook is very good, so I'm just writing it so that when we start doing the derivation from the point we left, we have some, you can say, what you call feeling of the thing at the background of our mind. Okay. A pulse decaying act as 1 by t⁻p for p greater than 1 should work in our case. In our case means you must be knowing, since the series summation n is equal to 1 to infinity 1 upon n⁻p does converge for p greater than 1. Okay, this I am not referring to, but I think you know from sequence and series. I think the first year course in mathematics must have done this test and everything, and there you must be solving questions, so I am not going into it. A faster time decay, so this is the premise, a faster time decay requires a slower decay in frequency. आप इसको फूरियर सीरीज से भी समझ सकते हैं. देखिए, अगर आपको शार्पर डीके बनाना है तो आपको मतलब यह है कि फॉलिंग रेट जो है सिग्नल का वो आपको फास्ट चाहिए. अब फ्रीक्वेंसी डोमेन में क्या होगा, जब तक आप हाइयर फ्रीक्वेंसी कंपोनेंट्स को लेकर इस सिस्टम को डिजाइन नहीं करेंगे तब तक ये शार्पर फॉल नहीं आएगा. आप फूरियर सीरीज कोफिशिएंट से समझ सकते हैं. अगर आप हाइयर फ्रीक्वेंसी कंपोनेंट्स के साइनोसॉइड्स को ऐड नहीं करेंगे, वो तो पीरियोडिक सिग्नल के लिए है, बट फूरियर ट्रांसफॉर्म से भी हम कंस्ट्रक्शन करते हैं सिग्नल का, क्योंकि इनवर्स फूरियर ट्रांसफॉर्म एग्जिस्ट करता है. तो वहां से हम ये चीज, मतलब ठीक है, एट द यूजी लेवल देयर इज नो नीड टू जस्ट dig too deep into it, but concept wise you can understand from the Fourier series that अगर आप higher frequency components को लेके नहीं चलेंगे तो unless you add components which are of higher frequency you cannot have sharper transitions. Okay, this you can see from the Fourier series construction of the rectangular waveform which has been given as an exercise in the lab as well. So you will realize that जो वो transition होता है square pulse का, ये वाली, इसको बनाने के लिए you require a lot of high frequency components. Still वो बन नहीं पाता है, उसमें I think you will study there is some effect, Gibbs phenomena and all these things. I think it was covered in signals and systems. So I can just refer you to that textbook or course for digging deep into it. So slower decay in frequency. Thus we need access bandwidth. Okay, beyond the minimum bandwidth dictated by the Nyquist criteria. To fix the problem associated with the signals. Okay, associated with this signals. So this is what is the point behind. Let us now we go back to the point where we left. So we started from this. So we were doing this, find a pulse PT that satisfies Nyquist's first criterion, that is, it should lead to zero RSI at the, or it should have a zero value at the sampling instance, and it should have a non-zero value at t equal to 0 and at other places. It means not at the sampling instance. And decays faster than 1 by t. So Nyquist showed that such a pulse requires a bandwidth which is kr by 2. It means minimum bandwidth से थोड़ा ज़्यादा और r से छोटा. r तो सब अपर लिमिट है. क्यों? क्योंकि r में आपका नेक्स्ट बिट आएगा. So let pt be the pulse, and the Fourier transform of it is p of f, where bandwidth of p of f is in the range r by 2 to r. Now we have at the start itself we have assumed. Now at this point I should say that the proof given by VP Lati is somewhat you can say tailored as per our requirement. Okay? Not very involved proof, a simple proof the author has given, because this is a very good undergraduate textbook. So at our level and for our needs, this proof suffices. Okay, this proof might have some, you can say, fallacies. I asked that at the start itself we are assuming this and we are proving the same thing. But if you go deeper, or if you need to have a more, you can say, professional way of presenting it, then you have to go to Couch's book for that. All are undergraduate tips. Okay, ऐसा नहीं है कोई भी इसमें ऐसा नहीं है जो आपके लेवल पे नहीं है, मतलब इतना हमें पता होना चाहिए. बट इसका प्रूफ थोड़ा सा आसान है, मतलब the way they have given is easy to follow from signals and systems. That's why we are taking it from that place. So the bandwidth of P of f is r by 2 to r. So we said that the requirement 1, or the Nyquist criterion, the first criterion can be stated like this. You can multiply the pulse P of t with this impulse train. Okay. I showed it to you that why this criteria 1 can be written through multiplication of, why this criteria 1 can be written through multiplication with the impulse train. Okay. So we showed it. Then we said, let us take the Fourier transform both these sides. So once we take the Fourier transform, you know that if at all this P of t is in multiplication with this, so in the frequency domain, P of f needs to be convolved with another shifted impulse train in the frequency domain, because we know that for the impulse train in time domain, in frequency domain, the Fourier transform is another impulse train, and that impulse train is an impulse train in frequency. Okay, so the same thing we used here, and we said that this should be equal to 1 or this should be equal to t of p. So we'll start from this point. Okay, continuing from last page of lecture 4. Okay. Now consider the range. Consider the range. Suppose हम लोग एक रेंज लेके चल रहे हैं 0 से r के बीच में. Okay. Over this range, only two terms only two terms, P of f and P of f minus r in the summation are involved. Okay, let me just write the summation for you. So summation was summation n is equal to minus infinity to infinity P of f minus n r must be equal to P of. Okay, so this was the condition we got, that for any pulse which needs to satisfy Nyquist's first criteria need to have a form like this. So we are now, since this f is the independent variable, so we are considering f over this range. Okay, so if we study it over, if we study it over, okay, because we said that P of f will have a bandwidth of r by 2 to r. P of f is a bandwidth, I think, r by 2 to r. So it means any number between r by 2 to r it has a bandwidth. So over this 0 to r, you can have the current is P of f and some interference, or you can say some overlap with P of f minus r. Okay, that is the first term will overlap from 0 to r. Okay, if we consider from minus r to r, then you have to consider P of f plus r as well. So यहाँ पे हम 0 लेके चल रहे हैं, तो इसीलिए दो ही पल्स इसमें या दो ही स्पेक्ट्रम इसमें आएगा. So this you should remember. So if we study it over this, so over, let me write it again so that if at all those who are studying from the notes know that over this summation can be written like this: P of f to P of f minus r must be equal to T. मतलब अगर इस डोमेन की बात करें तो उसमें ये जो आपकी इक्वेशन है ऊपर वाली, this should be this. Okay, this is this basically. So let us change a variable. So let f is equal to x plus r by 2. Okay, or x is equal to f minus r by 2. Okay, so then what we have? Then you can simply write it as p x plus r by 2 plus p of x minus r by 2. That must be equal to Tp for this less than r. Okay, why? Because we need to convert this range as well. So if we are having this change of variable, if we are doing f as x plus r by 2, so over our range x by r by 2 should be like this. This implies that x should lie between r by 2 and it should be minus r by 2. What does this mean? This means mod x should be less than. So I just done the derivation for this. I think this is very easy. You all can do it. But just for the sake of completion, I am doing it. Now using conjugate symmetry, this is what we know from Fourier transform. Conjugate symmetry property of Fourier transform. I am not writing it. If GT is real, so if you have a real signal, if GT is real, then G of minus f is equal to G star. Okay, this is one of the properties of Fourier transform. Okay, you can say property of Fourier transform. I am again writing it. I think this conjugate symmetry property is that of Fourier transform. So अगर आपका function real है, if at all your GT is real, then the Fourier transform is like this. It is conjugate symmetry. G of star f is same as G of minus f. Now what does this imply? This implies that if I talk of the magnitude spectrum, this is equal to. It means this is an even function. This magnitude spectrum will be even function. Okay. And the phase will be an odd function. Okay, this is yes. ये प्रॉपर्टी होती है, इसका प्रूफ हम लोग सिग्नल सिस्टम्स में भी करते हैं. एंड इफ एट ऑल यू फॉरगॉटन इट, देन यू कैन just go and see any standard textbook on Fourier transform, or for your case you can see Oppenheim, Wilsky or Simon Higginson motion systems book, and you will get this proof. So this is the fact. So हमने अज्यूम किया था कि पीटी रियल है. ऑब्वियसली पीटी रियल ही होगी. पीटी एक ऐसी पल्स है जो कि हम जनरेट करेंगे, जनरेट करके ट्रांसमिट करेंगे. सो इफ यू टॉक ऑफ anything which can be implemented, complex numbers is a theoretical concept. You cannot have iota in hardware. Okay? So PT has to be real. So since PT is real, the Fourier transform will satisfy this conjugate symmetry property, and you can write that P of r by 2a plus x plus P star r by 2 minus x. This must be equal to 3. Over mod x this thing. So this is the simple, you can say, this is the relationship which we get from this. आप इसमें क्या किया आपने? सिंपल r by 2 plus x, और इसको आपने माइनस को ले लिया, माइनस ऑफ r by 2 minus x. तो उसको आपने ऐसे लिख दिया. ठीक है. Now so this is the way Lathi builds this proof. Okay, so now if we choose, अगर आपने by choice PF को भी रियल चूज किया, मान लीजिए कि आपका जो स्पेक्ट्रम है वो भी रियल है, टू बी रियल वैल्यूड, and positive, then only P of F needs to satisfy the above equation. Okay. Now why? Because there won't be any phase term. If at all your P of F is the real, the magnitude only needs to satisfy this. No? There is no phase term. So if at all you do this star operation, so there is nothing is going to change from the star. Okay. So this says that this plus must be equal to T. There is one important catch, that this should be real valued and positive. Otherwise, ये valid नहीं होगा. It means if it is real valued and positive. अगर ये केस है कि ये real valued और positive है, so this equation is same as this. अब ये आपको सोचना पड़ेगा, and that I should leave it as a small homework. That if at all this is the case, it is real valued and positive, so does this implies this? If it doesn't, then we will definitely discuss it. It means if we can prove that this doesn't happen, then we can at least see that the author has done some mistake in proving this in this way. Okay, but I feel that this is fine, because if it is real valued and positive, if it is positive, then this P star r by 2 minus x doesn't have any you can say, let us see this. Suppose there is a complex number, or there is a number a, x is a, and a is positive. Okay, then mod x is same as a. What is x star? X star is same as a. Okay. So if x star is same as a, so mod x star is also same as a, which is equal to mod x. Okay, so that is what basically यहाँ पे लिखा है. तो आपने कहा था कि x plus sorry, it shouldn't be x, let us say y, because they are two different values. So we said that this should be like this, that y plus x star must be equal to t, tb. Let us assume that, so we have said that y and x comma y are, they are real numbers with positive, okay, r plus को belong. So दिस इज सेम एज सेम, ये बराबर ही आएंगे क्यों, क्योंकि अब मॉड वाई क्या होगा, वाई के बराबर होगा, दिस इज सेम एज वाई। और मॉड एक्स क्या होगा, एक्स के बराबर होगा। अब क्योंकि एक्स रियल है तो एक्स एक्स स्टार के बराबर होगा। सो बाय कंस्ट्रक्शन यू कैन से दैट दिस इज सेम एज दिस। If still, if you go back, you go through it, if you are not convinced or you have a better, you can say contradictory comment to it, then that would be pretty good, we can discuss. But with this basic explanation, I leave the further discussion to the class in general. It means after the class, you can all discuss this if you want. So इसका मतलब क्या है, ये इससे क्या होना चाहिए, ये important equation है। ये डिजाइन डिक्टेट करती है। ये डिजाइन कैसे डिक्टेट करती है हम इसको देखते हैं। लेट अस गो बैक टू द टेक्स्ट बुक एंड सी द फिगर देयर। ओके, सो व्हाट डज इट शोज अस? सो फिगर 7.13 वी शुड सी। सो अगर आपका पी ऑफ एफ जिसका जो मैग्नीट्यूड स्पेक्ट्रम है वो लेट अस से वो तो पॉजिटिव ही होगा, इस तरीके का है, और अगर मैं इसको शिफ्ट करूं मतलब कि दूसरी पल्स भी देखूं तो इस तरीके का सिस्टम आना चाहिए, इस तरीके। और इस बैंड के ऊपर इन दोनों का सम जो है वो टीबी होना चाहिए। ओके, जैसे कि एक हम इसको बना के देख सकते हैं। सपोज दिस इज योर फॉर्मूला, you must get this. Now if I add, suppose this is x1 signal and this is your x2 signal. What I want is that if I add at any t or all t between this, suppose 0 to t, if I add so the point to say is that if I add x1t and x2t in 0 to t, it should be a constant. इस तरीके की चीज को हमें जनरेट करना है और यही ये इक्वेशन है। अभी देखते हैं कैसे। इसके लिए ऑड सिमेट्री होनी जरूरी है। ओके, अभी ऑड सिमेट्री क्या है? सो लेट मी राइट। सो कर्व शुड हैव, कर्व हैज एन ऑड सिमेट्री about the set of axes, intersecting at point alpha, that is f is equal to r. नो, ये ऐसा क्यों होना चाहिए? देखिए ये क्या कहता है, ये कहता है कि भाई आपने जैसे p ऑफ x था, p ऑफ x है, आपको ये दोनों जनरेट करने हैं, तो कैसे करेंगे? एक बार आपने p ऑफ x को पीछे शिफ्ट किया, देखते हैं। लेट मी जस्ट ड्रॉ इट फॉर यू। सपोज यू हैव p ऑफ x and you want to generate p of x plus r by 2. So how will you do it? You will shift it to minus r by 2. जैसे सपोज आप मान लीजिए आपका पल्स है, so this is your pulse, this is p of f, so p of x, and this is supposed somewhat, let us take, or let us not do it right now. So I just shift it to r by 2, minus r. Then I need to generate p of r by 2 minus x. So it is simply, सबसे पहले फ्लिप करेंगे इसको। सपोज ये थोड़ा सिमेट्रिक फंक्शन है तो फ्लिप करने के बाद भी इसका रिजल्ट सपोज ऐसे ही, and then you will basically shift it towards the right. Okay, so suppose मान लीजिए कि ये आपका ऐसे है, तो अब ये अगर टीबी है, ये लेवल टीबी है, ये लेवल टीबी है, तो आपको चाहिए कि इस इंटरवल में ये है, इसमें एडिशन जो है वो टीबी होना चाहिए। इसके लिए इस पॉइंट के अक्रॉस, ये जो इंटरसेक्शन पॉइंट है, अक्रॉस दिस पल्स शुड बी पैरामीटर इट शुड हैव अ ऑड सिमेट्री। अब यही है कि इसके ऊपर हम डीप डिस्कशन नहीं करना चाहते, क्यों? क्योंकि वही बात है कि ये बहुत ज़्यादा फिर हम इसको प्रोफेशनली प्रूव नहीं करना चाहते हैं। ये होगा, मतलब दिस इज व्हाट विल हैपन, वी वांट टू इंट्यूटिवली अंडरस्टैंड दिस एट दिस पॉइंट, ऑल्दो दिस इक्वेशन टेल्स अस दिस, ये इक्वेशन ऐसा बता रही है ठीक है कि ऐसा होना चाहिए, सेम पल्स है उसका, ऐसा आपने शिफ्ट किया, एब्सोल्यूट मैग्नीट्यूड दिया, ऐड किया, टीबी होना चाहिए। So this dictates that this should have a odd symmetry about r/2. Okay, that is the point of intersection. That is alpha equal to r/2. We are not discussing further on this. That is what I was saying, that Lathi gives us the proof which is a mix of intuition and the fact. It means कि जो हम analysis कर रहे हैं और intuition का mix है। Okay, तो वही है ये राइट। तो हम इसको अभी आगे बढ़ेंगे जब हम इसको रीडिस्कस करें कभी आगे, और इफ एट ऑल यू गो थ्रू इट एंड सम ऑफ यू वांट अ डिस्कशन ऑन इट, देन वी कैन डाइव डीपर इनटू इट। ओके, नाउ इफ एट ऑल यू नीड टू हैव ऑड सिमेट्री, सो लेट अस गो बैक एंड सी दिस। ओके, तो ये चीज अब देखिए, आप इसमें ऑड सिमेट्री कैसे बताएंगे? अब r/2 के पास आपकी ऑड सिमेट्री है, so if at all I need to say that odd symmetry, so what will you do is that जो इसकी आगे की वैल्यू है वो इसके पीछे की वैल्यू के बराबर होगी। मतलब हाउ डू डिफाइन ऑड सिमेट्री? आई थिंक दिस यू मस्ट बी नोइंग, आई थिंक उसमें ज़्यादा जाने की ज़रूरत नहीं है, बिकॉज ऑड एंड इवन फंक्शंस यू आर ऑलरेडी टॉट। सो लेट अस मूव अहेड विद द प्रूफ देन। ओके, सो नोट दैट this requires p of r/2 must be equal to mod of p of 0 into 1/2. Okay? Why? Because both the pulses will add at this point. So ये जो point है आपका point of intersection है, इस पे TB/2 होना चाहिए, ताकि जब हम ऐड करें इनको, so at this value, at this point pulse values must be half of maximum. Okay. अगर आप चलिए, मैं फिर अब ऑड सिमेट्री बोला, आई एम नॉट फीलिंग दैट मच सेटिस्फाइड, लेट मी जस्ट डिस्कस ऑड सिमेट्री विद यू। सपोज जैसे कि अब आप ये देखिए, इफ यू हैव दिस कर्व, okay, अब if I have to draw the corresponding odd symmetrical, this is odd symmetry, suppose 0 है, so ये t पे जो वैल्यू है, let us say this is called as f of t and this is t of 1, this point, the value at f of t1 must be equal to minus of value of f of minus t. I think that is what we are told, must be equal to minus. So minus t1 suppose, और जो वैल्यू ये थी, सपोज ये वैल्यू a थी, तो यहाँ जो वैल्यू आएगी वो, ओके, सो दिस इज माइनस, दिस विल बी। सो शेप के मामले में अगर आप देखेंगे तो अगर ये इसका कर्वेचर ऐसा था तो उसका कर्वेचर ऐसा, सो दिस इज प्रीटी मच व्हाट इज यू विल सी हियर। सो नाउ अब आप इसको, आई थिंक विद माय एक्सप्लेनेशन नाउ यू कैन सी इट मोर क्लियरली, दैट देखिए x के आसपास, x के नीचे जो कर्वेचर है वो आपका इस तरीके का है, तो इसी को अगर आप मिरर लेके ऊपर में देखेंगे लेफ्ट साइड, मतलब लेट अस से इफ आई प्लेस अ मिरर एट r/2, ओके, लेट अस से इफ आई प्लेस अ मिरर एट r/2, कि अगर आपका ये है, इसमें आप मिरर रखिए, जस्ट प्लेस अ मिरर, in our 11th and 12th we are told that mirror kaha viewing position is. So if you place a mirror over here and whatever you see in the mirror you flip it, okay, and then you flip across it. मिरर में आप अंदर ऐसा देख रहे होंगे, ऐसा, अब आप इसी को ऊपर फ्लिप कर दीजिए तो ये आपका ये, that this is the way we visualize it. Okay, so this is the ऑड सिमेट्री। तो पल्स में ऐसा होना चाहिए, बस यही रेस कोसाइन डिजाइन है और ये इंपॉर्टेंट डिजाइन है। उसका एक रीजन है कि रेस कोसाइन पल्स आपको पता होना चाहिए, बहुत ही पुराना you can say a known thing in the community, and if you go for interviews for core companies and maybe not for the core companies or those companies who somewhat do design work for these core companies, they assume or they will ask you in the interviews if you know something about the Nyquist pulse. Nyquist pulse is the standard sync pulse that is which satisfies the first criteria with the minimum bandwidth, and then they will ask that if at all you increase the bandwidth, what can you say about the race cosine? So race cosine इस तरीके की pulse होती है, मतलब उसमें ऐसी ऑड सिमेट्री होनी चाहिए पॉइंट ऑफ यू कैन से इंटरसेक्शन के पास, तभी वो ऐड होके टीवी होगी। अब आप देख सकते हैं यहाँ पे। ओके, विद दिस एक्सप्लेनेशन आई थिंक इट वुड बी इजी फॉर ऑल ऑफ यू टू अंडरस्टैंड दिस। So let us now move ahead with the point. I think here we were. The bandwidth in hertz of PF is bandwidth in hertz P of F is R by 2 plus F of X. Anyways, we have already said that the bandwidth of P of F lies between R by 2 and R. So assume that the bandwidth of R by 2 plus some F of X is, where F of X is a positive number, where F of X is the bandwidth in excess of the minimum bandwidth R by 2. So we define one coefficient, it's R, which is excess bandwidth, divided by theoretical minimum, which is equal to Fx divided by R, and this is equal to twice of Fx into Tp, where Tb is what? 1 by R. I think I have already introduced this 1 by R. With bit interval, Tb is bit interval, okay, and if at all Tb is the bit interval, then obviously bit rate will be 1 by Tb. So a straightforward relationship, I think you must be knowing. So as f of x cannot be larger than R by 2. Why? Let us see this. Because we said that the bandwidth of the pulse has to be between R by 2 and R. If I am saying that it is a number in between, so any number in between R by 2 and R necessitates, or you can say forces, if R by 2 is any number in between R by 2 and R, just delete it, write it again more clearly. These are small details. I am doing it just so that if at all you are reading the notes. So if R by 2 plus X is any number in between this, it forces X between R by 2. Okay. तो पता है आपकी अगर X ये नंबर अगर R by 2 और R के बीच में होना चाहिए, तो जो X की वैल्यू है वो 0 से R by 2 के बीच में हो सकती है. So Fx cannot be larger than R by 2. Okay. So R is not. So ये एक बहुत इंपॉर्टेंट वैल्यू है. ये आपसे अक्सर पूछी जाती है, कहीं भी आप जाएंगे कि भाई एक्सेस बैंडविड्थ टू थ्योरेटिकल मिनिमम बैंडविड्थ का रेशियो क्या है. दैट इज R. दिस विल बी ऑलवेज लाइन बिटवीन 0 to 1. So if this is the case, so in terms of R, we can write f of x. So f of x is nothing but, okay, why? Because from here you can see from 2 fx is equal to R. So transmission bandwidth. So bandwidth of P of f is P of t is equal to R by 2 plus R, okay, which is equal to 1 plus R into R. This is a very important basically equation. इसी से आप I think you can just suffice it, but you need to know कि I कैसे, how did you come to this point. उसी के लिए हमने derivation थोड़ा basic में किया है. So R is the role of factor, is a popular name given to it. Basically it is called as, okay, and also expressed in terms of percentage. In terms of percentage. Okay, so pretty much जो derivation हम लोगों को करनी थी वो इतनी ही सी थी, छोटी सी derivation थी, in the sense कि we just wanted to know that कि अगर कोई ऐसा पल्स एग्जिस्ट करता है या नहीं करता है जिसमें आपका जो यू कैन से कि जो रेट ऑफ फॉलिंग है वो ज़्यादा हो. अभी तक हमने ऐसा पल्स मतलब कुछ से डिफाइन नहीं किया. रेट ऑफ फॉलिंग पे हमने कोई अभी इस प्रूफ में कोई बात नहीं करी है. बट हाँ, अगर ऐसा पल्स चाहिए, मतलब लेट अस सी व्हाट Nyquist said. I think what we wrote in our last class that Nyquist showed that such a pulse requires a bandwidth of kr/2 with this, which decays faster than. अभी हम इसको और आगे डीपली स्टडी करेंगे. अदरवाइज if at all things are not very clear, then we will discuss it once more in the forthcoming lectures. Okay. So for example, if P of F is a Nyquist first criterion, spectrum with bandwidth that is 50% higher than the theoretical minimum its role of factor R is equal to 0.5 or 50%. So now you can see that P of F can be generated as a unit impulse response, of a filter with transfer function P of F, P of T. This should be clear. This should be small. बेसिकली अगर आपके पास एक फिल्टर है जिसका ट्रांसफर फंक्शन P of F है, फिल्टर ट्रांसफर फंक्शन मींस उसका जो इम्पल्स रिस्पॉन्स है उसका अगर आप फ्रीक्वेंसी डोमेन में स्टडी करेंगे तो P of F होगा. तो बेसिकली एक फिल्टर है, मतलब ये कहने का मतलब है कि जो पल्स है वो जनरेट कैसे होगी, एक फिल्टर से जनरेट होगी और फिल्टर जो टाइम डोमेन हो P of T है और उसका फ्रीक्वेंसी डोमेन में रिस्पॉन्स P of F है. Now, but here is a catch, okay? But because P of F is 0, हम लोगों ने जो यहाँ स्टडी किया है, so whatever we study, we said that it is 0 after some value. यहाँ पे 0 या RB के बाद तो 0 0 होना ही है इसको, that is what we have said. बट ये हमने एक स्टडी किया था पहले लीनियर क्राइटेरिया कि अगर फ्रीक्वेंसी में भी अगर आप कहते हैं कि ऐसा कोई स्पेक्ट्रम है जो कि 0 है आफ्टर सम फ्रीक्वेंसी बैंड, देन इट इज आल्सो नॉट प्लेसेबल. ओके, over a frequency band it violates Palavinar, criteria, and analyze. Okay, that is what we just took it. We didn't prove it. Not required at this point. बट अब हम क्या कर सकते हैं, हम रोल ऑफ जो है थोड़ा ग्रेजुअल है, ठीक है, लेट अस राइट हाउएवर रोल ऑफ इज ग्रेजुअल, रोल ऑफ is gradual and can be closely approximated by practical filter. It means ठीक है, ये theoretically हम ऐसा पल्स मान के चल रहे हैं कि एग्जिस्ट करेगा, इसमें ये जीरो हो जाएगा बिल्कुल, बट क्योंकि ये रोल ऑफ जो है वो थोड़ा सा ऐसा है कि जो स्मूथ फ्रीक्वेंसी डोमेन में, तो जो प्रैक्टिकल फिल्टर्स हैं जो ऐसा नहीं है कि एक लेवल के बाद बिल्कुल जीरो आउटपुट देंगे, थोड़ा आउटपुट देंगे जो बहुत कम एम्पलीट्यूड का होगा, वो उसको आसानी से अप्रोक्सीमेट कर सकते हैं ताकि ये क्राइटेरिया अप्रोक्सीमेटली हम सेटिस्फाई कर पाए समेशन वाला जो this okay. So it can be closely approximated by practical filter. See, this is the basically beauty of you can say the engineering design, that all the courses are somewhat interlinked, and that's why it has been arranged in this manner. That first you need to know signals and systems, but our notion has been that at the UG level we should not understand things somewhat deeply. This is not right. We need to know at least कि ये कैसे हुआ, कहाँ से आया, ठीक है, वो सपोज हमने कहा पहले भी नहीं, उसका प्रूफ करना इतना रिक्वायर्ड नहीं है, बट ये जानना जरूर है कि क्या ऐसा हो सकता है। इसका मतलब है कि क्या हम फ्रीक्वेंसी डोमेन में ऐसा स्पेक्ट्रम रियलाइज कर सकते हैं कि वो एक फ्रीक्वेंसी के बाद बिल्कुल जीरो, तो पहले भी इन्होंने कहा नहीं ऐसा नहीं हो सकता, इसीलिए देयर इज ऑलवेज अ गैप बिटवीन थ्योरेटिकल फिल्टर डिजाइन एंड प्रैक्टिकल फिल्टर। तो रीजंस हैं उसके पीछे, नहीं तो हम लोगों को ये पता ही नहीं चलता है कि ये ऐसा क्यों हो रहा है। दैट इज यूजुअली लेवल वी मस्ट नो कि भाई ठीक है ये इस वजह से हुआ, इन्होंने ऐसा कहा तो ऐसा हुआ, ठीक है, प्रूफ ना जाने। अब वैसे ये थोड़ा जो हमने ऊपर किया है ये इज नॉट वेरी वेरी गुड प्रूफ, बट इट टेल्स अस अ फ्यू थिंग्स अबाउट द पल्स डिजाइन। And I deliberately did it from Latif, assuming that we should not dive that much deep into these proofs unless required, at least for this, because इसमें बस हमें जो ये और सिमेट्रिकल कॉन्सेप्ट था वो जानना जरूरी है, वो हमने ऊपर थोड़ा बहुत किया, and then we can move ahead and design our race cosine pulse. Okay. So let us see the family of spectra. So now we are going to do the raised cosine one that satisfies Nyquist first criteria. Criteria is and the roll off is or decay rate. The decay rate is greater than 1 by t. Should be mentioned here because otherwise the first pulse is the same pulse which will satisfy it. And the decay rate is greater than 1 by t. So this is your raised cosine spectrum. Okay, one of the very very important pulse design. So this is this one. It takes a value 1 for mod f less than r by 2 minus f of x. Then it takes a value 1 by 2, 1 minus sine of pi mod f minus r by 2 divided by 2 of x. For mod f lying between r by 2 minus f of x finally it is 0 for mod f greater than r by 2 plus f of x. So this can be seen from figure 7.14. Basically ये जो PT है आपका, that is what I think this plot is for raised cosine only, right? Check. Okay. So you can see that जो सिंपल है डार्क वाला है ये सिंपल है. अब उसका आप देखिए कि कितना देर में डिके होता है. बट इफ यू सी दिस डैश लाइन वन, सो यू कैन सी कि माइनस टीबी से टीबी के बीच में देयर इज समवॉट अ सिमिलर कर्व, बट एज सून एज यू exceed dB, you will find that this decay is very sharp. You can clearly see the difference. At this point, this has touched 0, but this is still taking quite a large value. The sync pulse. This darkened one is the sync pulse, and this is the raised cosine pulse for different values of small r. So you can clearly see, or here it is written Nyquist criteria pulse is satisfying, but I know that this is somewhat they plotted the raised cosine. तो इस तरीके का हमें स्पेक्ट्रम चाहिए और इस तरीके का हमें टाइम डोमेन बिहेवियर चाहिए that this pulse should decay fastly. Okay, I need to just. Okay, so that is what I just said. So you can just read that figure 7.14a shows 3 curves from this family, which is given above, or I have just written. Yeah, I need to say one more thing, that there is some basically error here. This is not correct. So if you have BP Latin text, you are reading through it, I think this is somewhat incorrect. I have corrected it and written it afresh in the notes. This is the correct domain. Okay, so थोड़ा सा erroneously ये domain given है. In all good books, you will find some typos. Sometimes the authors basically come out with an errata which tells you the errors. I didn't check the errata of Lati because I have the errata for couch, but this you can obtain from the net if you want. But we have just corrected it. This should be mod f lying between r by 2 minus fx with r by 2 plus fx with mod f lying. Okay. So corresponding to r equal to 0, fx is equal to rp by 4, that is r equal to 0.5 and r equal to 1. So for 3 values of r, they have basically plotted it. For r equal to 0, it is the standard, I think, the same pulse. And for others, they show that what is the decay rate. Okay. So the respective impulse responses are shown in B. It can be seen that increasing fx or r improves PT. That is, more gradual cutoff reduces the oscillatory nature of PT and causes it to decay more rapidly in time. Okay. नहीं, more gradual cutoff का मतलब है frequency domain. अगर आपने बिल्कुल sharp cutoff किया है this way, so it will have a lot of oscillatory nature. It means कि high frequency components नहीं होंगे. But अगर आपने gradual, let us say you have designed the spectrum is somewhat gradual, so it has higher frequency components as well. So this will lead to a, you can say, sharper fall, or this can lead to a sharper fall in the time domain function. That is what we want. Now for f of x equal to r by 2, that is r is equal to 1, we have, if at all we assume or we take, so we can simplify the above expression and we will have p of f as 1 by 2 1 plus cosine phi f dB into the rect function f of f upon 2. ये बहुत आसानी से आप डिराइव कर सकते हैं. I just checked it because I need to check a few things before I present. That's why I do it in rough, but I don't think I need to do it here because this is quite straightforward. I checked it. Okay, you can just derive it. This can be easily written like this. So if you see this p of f is this, then just use some inequality. Some equality of cos function and its square. So you can write it like this: cos square phi of f dp by 2. This rect function of f of p. Basically, I have replaced 1 by r with dp. So this check I am not doing. I think you can do it. So this is known as, this is known as the raised cosine characteristic. Raised cosine characteristic in the literature. And the inverse Fourier transform, or the PT, is inverse Fourier transform of P of f. This you observe that P of f is right now a real function, okay, and that too you will see that this is cos square that is positive. This P of t is, so somewhat it is linked with what we did above. We basically started with assuming that P of f is real and positive, so we came up with something like this. That is r into cosine of pi r t divided by 1 minus 4 r square t square sinc of pi r t. This is the time domain, this function for this class. If you have any comments or if anything to say, anything to you can discuss, you can just unmute and say. You are most welcome to do that. And if at all you need to discuss something, we can have an offline discussion like this after the class. So what is the features? Let us see the features of such a pulse design. Today I am just somewhat rushing through a few, one or more, two small things. I am not saying things about them. Maybe I will talk about them in the next class, because it is important to first have a development and then we can go back and see a few of the pending issues. Okay. So later, what are the features of this raised cosine? So the bandwidth, because R हमने assume किया था, I think here we said that R is 1, so Fx is R by 2, so bandwidth consumption would obviously be R. Okay. So bandwidth of pulses, the maximum possible, versus R. That's okay. Second, value of so at t equal to 0, value of pulse is R. Pulse is R. I think this you can clearly check. If you put t as 0 here, so cos 0 is 1, denominator is 1, and sinc of 0 is 1. So it will have value of R. Is R at t equal to 0 and is 0, and is 0 not only at all the remaining signaling instants, at all the remaining signaling instants, but also at points, midway between all signaling instants. We will see it, okay? Let us see this. So let us check for R equal to, you can say, I think we are studying R equal to 1. Yes, it is. So heavy dashed curve, so this heavy dashed curve you can see. तो ये वाला डार्क कर्व है, आप इसको टाइम डोमेन में तो ये है, बट आप फ्रीक्वेंसी डोमेन में देखिए क्या हो रहा है. मतलब सॉरी, दिस इज द फ्रीक्वेंसी डोमेन, सी इन द टाइम डोमेन. तो दिस पल्स इज 0 एट दिस पॉइंट आल्सो. सिग्नलिंग इंस्टेंट तो 0 है, जैसे कि 0 पे ये वैल्यू आरबी लेता है, इस पे 0 है, इसके साथ सेकंड टाइम इंस्टेंट पे भी 0 है सिग्नलिंग पे, बट इट इज 0 इन बिटवीन एज वेल. दिस इज व्हाट वी हैव written. Midway between all signaling instants. Third point, which is important, it decays rapidly. as 1 by t cube. Okay, it decays rapidly as 1 by t cube. As a result, the raised cosine pulse, or you can call it as the RC pulse or RC filter. RC pulse. So I must mention this is RC. RC pulse is relatively insensitive to deviations of R, that is sampling rate. Deviations of R, sampling rate, timing jitter, and so on. So ये तो चाहिए था हमें कि अगर शार्प फॉल हो तो अगर हमारा थोड़ा सा सैम्पलिंग टाइम इधर उधर भी होगा, जैसे कि आप इस पल्स में देख सकते हैं, इफ एट ऑल माय सैम्पलिंग टाइम इज नॉट एट सपोज टीवी, इट इज समवॉट हायर देन टीवी. सो ये जो वैल्यू है इस पल्स की बहुत छोटी है, बहुत कम वैल्यू है, तो जो अदर पल्सेज होंगी वो भी बहुत कम मैग्नीट्यूड की होंगी, तो दे वोंट बी कंट्रीब्यूटिंग दैट मच टू दिस सैम्पलिंग एक्सटेंट. Instead, if you check on the sync pulse, so sync pulse is assuming larger and larger values. यहाँ तक काफी इसकी वैल्यू बढ़ी है. सो अगर इस sync pulse के साथ आपका टाइमिंग जिटर होता है या आपका सैम्पलिंग रेट थोड़ा बदलता है, तो यू विल हैव अ लार्जर इंटरफेरेंस. सो दिस इज व्हाट वाज द प्रीमाइस ऑफ दिस डिजाइन. ओके, in the last thing which is very important to, you can say, somewhat conclude this section, is this note which I will be writing. So once this is done, we can I think close for today. So the note is that pulses received, so this is important to note, pulses received, we can have a detailed discussion or a small discussion in the next class on whatever we have done, because we have left a few things in between. Once the development is done, we will discuss it somewhat for 10-15 minutes. Okay. So pulses received at the detector input. The detector input should have the form for 0 ISI. Now why are we saying it? अभी तक हमने जो ऊपर काम किया, हमने एक बैंड लिमिटेड चैनल बनाया था, और वो बैंड लिमिटेड चैनल ऐसा था कि somewhat that it was passing some frequencies lying between -W to W, and then were terminating all the frequencies greater than W. But this channel of us would be band limited, but may not be of this ideal shape. Okay, so उसको कैसे हैंडल करना है? तो अल्टीमेटली 0 ऐसा ही आपको रिसीवर के इनपुट पे चाहिए. ओके, बिकॉज चैनल इज नॉट आइडियल. Down, because channel is not ideal and not ideal, that is distortionless, you can say distortionless. The transmitted pulses should be shaped so that after passing through the channel, with transfer function HC of f, okay, they will be received with the proper shape. They will be received with proper shape. Such as raised to samples, okay, such as RC. at the receiver. Okay, we will discuss somewhat in a more involved manner in the next session. Hence, the transmitted pulse Pi of t, that is, if we transmit Pi t, should satisfy. मीन्स अब जो आप ट्रांसमीटर पल्स लेंगे वो रेस कोसाइन नहीं लेंगे, आप वो पल्स लेंगे जो ये सेटिस्फाई करेगी. Pi of f into hc of f, this must lead to a raised cosine pulse. This is RC. This is at the transmitter. क्योंकि चैनल नॉन आइडियल है, चैनल HCF है. ठीक है, हमने जो अज्यूम किया था ऊपर वो माना था कि भाई आपका चैनल जो है एक बैंड को पास करता है, बाकी को टर्मिनेट कर देता है. ऐसा नहीं है, चैनल एक अपना वैलिड रिस्पांस होल्ड करता है. मतलब ठीक है, -P से B को मैक्सिमम को पास करेगा, बट जरूरी नहीं है कि वो सेम एम्पलीट्यूड का पास करे. इट कैन हैव अ शेप लाइक दिस एज वेल, like this sort of a shape. So this is suppose your HCF. So ultimately जो प्रोडक्ट यानी टाइम डोमेन में कन्वोल्यूशन होगा पल्स का फिल्टर के साथ, चैनल फिल्टर के साथ, तो फ्रीक्वेंसी डोमेन में मल्टीप्लिकेशन होगा. तो अल्टीमेटली जो मल्टीप्लिकेशन है दिस शुड लीड टू P of f. तो जो ट्रांसमीटर पल्स डिजाइन है शुड अल्टीमेटली लीड टू अ पल्स that is raised cosine at the receiver. So this is, I think, what I wanted to say for today. If at all there are any doubts, you can